Hello, lovely people. Today we will be talking about TS parameters and impedance graphs, and I'm going to show you how to measure them and how to find everything by yourself for a very cheap. Okay, so since I got these Alpine drivers, again, thank you very much, Frank, for HEPAKing for sending me these. These DP series, there's absolutely no information about them online. I can find the TS parameters for the status and for all the other drivers, but there's nothing for this. So I need to find out the TS parameters for these because I just like to know stuff. I like to have as much information as possible about the stuff that I'm using. So in order to find out TS parameters of any kind of driver, whether it be a mid-bass, mid-range, or a tweeter, or a subwoofer, or whatever, you need to measure the impedance of that specific driver. Now, what is an impedance? We are very familiar with resistance of a driver. So here I have my multimeter connected directly to this Fatal Pro 6FE100, and the impedance, not impedance, the resistance is showing 5.3, 5.4 ohms. Yeah, it's 5.5 because, like, when you're talking, the speaker itself acts as a microphone, and if you touch the cone, see, the resistance goes all over the place. So you have to, when you measuring the RE, the resistance of a driver, it has to be quiet and still, and this shows about 5.5 ohms. Now this 5.5 ohms is on DC, so it's 0 hertz AC current, basically when you have DC. And the resistance depends on the frequency, because a speaker is a reactive load. It's not a static load like a typical resistor, which you can see like here. Typical resistor. For a typical resistor, the resistance doesn't depend on frequency. For a speaker driver, it depends, and that resistance that varies depending on the frequency is called impedance. So resistance kind of resists the current flow, and impedance impedes the current flow, hence the name. Now, in order to measure the impedance of a driver, we need something. The most common thing that people use and is widely available is called Dayton DATS, which is a small little gadget. You can buy it for, like, I don't know, $100, $150 depending on the version. And basically it allows you to measure the impedance of any kind of driver. What I have here is a poor man's version of the Dayton DATS, which didn't cost me literally anything, just a few wires, few connectors, and one resistor. So how to make this is very simple. If you open REW and you go to help, show help, and here in the search bar you put impedance, and here you have impedance measurement, and this is the actual circuit which you need to measure the impedance with REW. So what you need is one output, which I have here, one output, and I need two inputs, left and right. I have two inputs with some connections and resistor, which my connections are here, and this is the resistor. And basically this is Dayton DATS for free, because if you have an audio interface that has two inputs, you already have everything that you need, and you just need to make this little circuit. And you can find the diagram here, and you can make it yourself. And if you have like an audio interface, you can make a budget Dayton DATS, and you can measure impedance of any kind of driver. Now, all the TS parameters of the driver are derived from the impedance plot, because the impedance plot shows you how the driver depends, how it reacts to any kind of frequency, and TS parameters are just mathematical equations that you can manipulate and calculate one from the other. And what we need is to have two impedance graphs. One is in free air, which is like if you just have a driver like that. I'm gonna turn it upside down, just like that. And you need a second impedance graph. So there's actually two ways how you can measure the TS parameters. Again, if you go to REW and open tools, and down here you have tells more parameters. And if you open this, there's methods. Those two methods, this added mass method and sealed box method, and we're going to be exploring both of them. So since I have this test enclosure made already, it is a sealed enclosure. I calculated the volume. It's 16 liters sealed enclosure, and it's just perfect for this measurement to have driver in the box, and it's a sealed box. Now the second method is added mass. For that, you need to add some kind of mass to the cone, attach it somehow, so the cone would be heavier when you take those measurements. So what I do, some people use blue tack, some people use like tape or something. What I decided to do is to use neodymium magnets. Yeah. So I have this, it's a precision scale. If I turn it on, because you need to know the exact weight of the weight that you're adding. So if I stick this, it shows me 9.94 grams. So basically it's 10 grams of added weight. And I added, it's impossible to do with one hand, so let me add it, I'm gonna show you. And I add it just like that. So basically you have magnet there and magnet there, and then basically if you use blue tack, it might leave some residue. If you use tape, it might leave some glue, but like magnets, they don't leave anything. So this is basically added mass. And what we need to do is we need to make an impedance sweep with REW. So I have everything set up here already. I'm going to just demonstrate you how to do this. You go to Measure tab, and here you have two options on the top. So there's SPL and there's Impedance. So if you choose Impedance, again, similar to regular measurements, you choose the level, name. Here you have to calibrate your thingy, what you made. Again, it's all in the manual, and you can choose however long the sweep you want it to be. So let's choose this one for now for 5 seconds, just as a test. Yeah. And you can check the levels. Yeah. It's working. And now I'm going to do the sweep. So if I start and shut up. And that's my sweep. So this sweep is with added mass. So let me remove that mass and let's take another sweep. Okay, just remove the mass because I cannot do it with one hand holding the phone at the same time. You need two hands. So now it's with no mass, no nothing, in free air. And we're going to take another measurement exactly the same way. Nothing changed. And here I have two measurements. Yeah. So one is with, so this is plus 10 grams, and this is in free air. So you can see we're gonna jump into the laptop. Just now I'm showing you how to do everything, but we're gonna jump into the laptop and analyze everything because I will be measuring all of the drivers. So two mid-bass, two mid-range, two tweeters, same here. I have the SB17s waiting, I have this, I have the peerless mid, so there's gonna be loads of measurements and loads of drivers. And we're going to be testing both methods for calculating the TS parameters. And exactly the same way, just this driver goes into that box. I connect the wires and do exactly the same sweep and have another measurement with the box. So for each mid-bass driver, because this mid-bass is 6.5 inch, the box, for each mid-bass driver, we're gonna have 3 measurements: free air, in box, and with added weight. But for mid-range, we're gonna have only free air and only added mass because I don't have an enclosure to make. And we're gonna be comparing what is the difference between the TS parameters calculated with REW using the box method, the added mass method, and we're going to compare them with the factory parameters that are provided for some of these drivers. One more thing that I forgot to mention, when REW calculates the TS parameters, it doesn't matter which method it uses, either added mass or the sealed box, it needs some extra stuff. So one thing it needs, if you're using the sealed box method, it needs the box volume. If you're using added mass method, it needs the added mass in grams. So in my case, it was 10 grams, and the volume of this enclosure is 16 liters. And another thing that it needs is a voice called DC resistance. So is the one that you are measuring with a regular multimeter. So for this specific driver, it was 5.5 ohms. And another thing, it needs the effective area of the cone. So in order to measure that, we need to do, if you don't have it in any kind of spec sheet, you take the ruler and you're measuring from not half, but a little bit less than half of the surround to the other side. And here you have about 13.4 centimeters, so 134 millimeters. For my American friends, close to 5.5 inches, a little bit more. And you convert this diameter into the surface area using a online typical any kind of formula, and you enter that as the effective area. Okay, so now we can jump into the laptop. So I have loads of measurements here. I have actually 39. Again, we're not going to go through all of them. And before we jump into the actual TS parameters to calculate them, let's have a look at the impedance sweeps and graphs and just try to see what we can find out just from the impedance graph. So this is the Fatal Pro 6FE. As you can see, it has one peak. So this peak is at the FS, which is the driver's resonance frequency in free air. And if I have the same measurement in a box, which is this, you can see that FS shifts. Actually, let me change the color because it's very similar. Something like that. There we go. So you can see if you put a driver in a closed sealed box, the resonance frequency shifts and it's called not FS anymore, it's called FB. From the free air impedance sweep, you can find out almost all of the parameters. And in order to calculate some extra parameters, such as like the moving mass or the VAS or some other stuff, then you need either added mass, either in a sealed enclosure. So this specific driver, Fatal Pro, you can see it has a smooth impedance. However, here at about 880, 900 hertz, there's a little bump and there's another bump here. An ideal driver will have this area absolutely smooth with no issues. Let's have a look at SB, not this one. For example, this SB Acoustics. You see, it's absolutely smooth, maybe a little bump here, but not much, but not as like this. So the smoother the impedance graph, the less issues the driver will have potentially in the frequency response. And just comparing these two drivers, we can see already that the SB Acoustics has a lower FS, which is like 45 hertz, and lower resistance because the SB Acoustic is a 4 ohm driver, and you can see here it shows 3.5 minimum, and the Fatal Pro is an 8 ohm driver and it shows 6.2 ohms. So you can see straight away that the resistance is different. And what else you can see is this rising top end. So this rising top end kind of defines the inductance of the driver. The higher the inductance, the steeper and faster this rise is. So when comparing these two drivers, we can already see that the SB Acoustics has a very extremely low LE value inductance, and the Fatal Pro has a higher LE value than inductance. And inductance is, they say, one of the main factors that corresponds to distortion. So the lower the inductance of the driver, the lower the distortion of the driver, and the higher it can play with no issues. Now let's have a look at the same driver in a box. If I put it in the box, as I mentioned, the resonance frequency changes. And the other thing you can see here there's little blips appear out of nowhere. So this is impedance graph in a box, and these are the standing waves or resonances that are happening inside the sealed enclosure. And this tool is amazing if you like building home speakers and you want to troubleshoot like frequency response issues that you have. So if I would apply some damping in the box, like putting some like polyfill or something, these blips would go away. And these blips appear in subwoofer boxes as well. However, they appear in higher frequencies, like above 200 hertz. So that's why if you would do impedance sweep on a subwoofer, and even if you're gonna see some blips like at 200-300 hertz, they don't matter just because the subwoofer doesn't play that high. Subwoofer plays like below 80 hertz only in this region. So anything that happens here doesn't really matter. However, for full ranges, boxes like bookshelf speakers, we have a mid bass playing all the way up to like 3K or something, these matter a lot. Now, if I take, for example, the status, one of the status drivers here, it is a 4 ohm driver, it's fine, and you can see these little blips. So it has one blip at about 280 and another blip at 1K. And if you saw my previous video where I showed you the frequency response of this status driver, at 1K it has a massive hole, and this blip here appears on the impedance graph. So we can say that that hole in the frequency response and this blip is a driver issue. And it's not nothing to do with the phase plug that in the very beginning I thought, but it's a driver issue itself. And we cannot do anything about it to fix it, really. So that's the status. Let's have a look at the DP. On a DP. So DP driver again, it has issues like 760, 780 in this area. It has some issues comparing to status. So comparing these two drivers, the status is the green one and the DP series is the purple one. You can already see that with no calculating TS parameters, nothing, just by the look of this, you can see that the DP has a slightly lower FS. However, the status has lower LE value, so it's lower inductance driver, and potentially it has less distortion. And the distortion measurements are done already, and you can see in this area again, it has some issues. Now let's have a look at some mid-ranges. So status mid-range, nothing really special, all smooth all the way. The only blip is here at about 18K, which doesn't matter. It's tiny blip here. FS at about 160. DP mid, there you go. So DP, similar, a little bit higher inductance, and the resonance frequency is much lower compared to the status. However, DP has some issues here because you can see a little blip at 1.7 and at 5K. So 5K is not that doesn't matter because it's going to be crossed below that. But like this, it's going to have some issues in the frequency response probably. So status, DP, where is my peerless in free air? So peerless, again, it's an 6 ohm driver, I believe, so it's a bit higher the resistance, higher LE, you can see straight away, and low Q. So again, this is a perfect example of Q. Even just looking at these two graphs without any TS parameters, you can see that peerless has a much lower Q because this peak is spread out more widely. And the DP has a much higher Q because it's more steep and more narrow, and the LE value is different. So mid-bass, mid-ranges. The other thing that we can have a look is the tweeters. So if you measure the tweeters, for example, the DP tweeter, so this is a typical metal dome tweeter, and you have one peak at about 1.9K, and this is the FS of the tweeter, 1.9K. So I would say it's a bit high because you would ideally want to cross it lower than that. So higher than that. So you need to cross like maybe 3.5K. The status tweeter, for some reason, it has two peaks on both of these tweeters. It has two peaks, one at about 2.5, and the other one is 1.5. If somebody can explain this to me, please do, because Alpine mentions something about this tweeter having a rear tuned chamber, so it kind of acts maybe as a ported tweeter, and that's why it has two peaks and a valley in between at 2K. I don't know. If somebody knows more, please comment below and tell me about it. And I have this SH is the shitty tweeter that I have, and the shitty tweeter has an FS of 3K. So this is, if you remember, is from a coax set of Kicker KS. It has some passive crossovers applied, and yeah, 3K FS, so it cannot play low at all. Now let's have a look at how we actually calculate the TS parameters. So if I open tools, TS more parameters here, and let's choose, for example, sealed box. So sealed box, first you need a free air measurement. So let's take this one, Fatal Pro, free air, just like that. And the second one is going to be my sealed box measurement. So sealed box is this one, box. And the box has 16 liters. The RE is measured with a multimeter 5.5 ohms, and I'll calculate it the area of 143 square centimeters. And if you click calculate parameters, it's going to give you all of these numbers here. And we're not going to go into these now because I have a separate sheet for them. So these are the numbers for one driver in a box. If you choose the other added mass, again, the free air measurement is exactly the same, and then you choose the added mass measurement, which is different. So I named it plus 10 grams, calculate the parameters, and it's going to give you another set of parameters. So what I did is for every driver, I did this, and then I put everything in here. I know there's a lot of numbers. We're going to go through them, so don't worry, don't get scared. So I have SB17, we have the factory parameters that are in the spec sheet, and then calculate it. First driver, second driver, and using both methods, mass method and box method. And exactly the same for all the mid-base drivers. And at the bottom, we have the mid-ranges. So that the boss, the shitty one that we have, peerless, that has the factory parameters, status, mid-ranges that has, again, factory parameters, not all of them, and the DP series that doesn't have anything. And now let's just have a look very quickly. SB17. So the biggest differences is that I notice in the FS. So the factory say that's 30 Hertz. From my measurements is 41 and 44. The QMS, QS, and QTS kind of similar. However, the QTS I measured higher at 3.5 and 0.49, which is a bit more than 0.28 that it should be in the factory. I don't know why. The mass of the driver calculated very similar, 12 grams, 12 and a bit, 13 grams, very similar. And CMS is a bit lower. So CMS is like the softness of the suspension. So according to my measurements, it's stiffer than from factory. Exactly the same VAS. So VAS and CMS, they're very connected together. And if one is big, the other one is big as well. BL is the motor force, similar to the factory specs. And the difference between the mass method and the box method, you can see here, it's not a big difference. Very, very slight for both drivers. And we have exactly the same for all of these drivers. So the most surprising is this Fatal Pro that factory drivers match the ones that are calculated extremely, extremely well. So I have FS 6169, then QTS 0.55, 0.59, moving mass 14, a little bit less, 12, but it's very, very similar. So we can say that, and again, all the drivers that come from factory, they're not gonna match the factory specs because they're not made like totally and completely identical. They will be slightly different, and here we can see these differences, especially if you break in, if you use the driver for a long time, these specs might slightly change as well. So the most important bit for me is the DP, the ones that don't have any parameters, comparing them to the status. So with the status, we have FS claimed 62, however, it's a bit higher at 75 and 78. Maybe after playing this drive for like a year or so, it's gonna loosen up a bit and the FS is gonna go down, but now it's close to 80, 75. The DP series has a lower FS, slightly lower, not much, 70, 75, like 10 hertz lower, 5 hertz lower. Yeah, it's not much. Now the QTS is this one that allows us to play the driver in free air. So the SB Acoustics, as you know, it has a low Q, so it's not ideally suited for IB, but you can work with it. The status claims that it has 0.55, however in reality it's a bit more, 0.6566, so it's perfect for IB. Same with DP, it has 0.6 and 0.66, so very good for IB in the doors. Moving mass, so status has claimed high moving mass, 18 grams. 18 grams for a 6.5-inch driver is quite a lot. However, the status has a much bigger coil compared to all the other drivers. It doesn't have a dust cap, but the coil is massive to absorb the extra heat. So I assume that the extra mass is due to the bigger coil. However, measured mass is slightly lower, 16-14 grams. And the DP, again, 14, 18 in the box, and 14 with added mass method. So which one is true? I don't know, but similar to the status driver. Carbon fiber, similar cones, similar looking cones. What else? BL, one of these. So status is 6.4, so it's quite big, quite strong motor for a 6.5. Same with Fatal Pro. So Fatal Pro handles 100 watts RMS and it's made for abuse. And Status claims to have 6.4, and by measuring, depending on the method, it varies from like 4 all the way up to 6, but it has a lot of motor force. Same with DP, 6.5 by 5.7. And the SB is a bit lower, 5, 5, measured 4, 4, 6. So I kinda think that if you have a higher moving mass on this status with a higher coil, you kind of try to compensate it with a higher motor force, which literally to putting a bigger magnet to have more control of it. Now LE, another surprising, the inductance is SB Acoustics has extremely low inductance, and we know that it plays very high. The Fatal Pro has 0.5 millihenries, which is not bad, but not very good. Similarly, DP has a higher inductance, similar to the Fatal Pro. However, the Status has extremely low inductance, very similarly to the SB Acoustics. For some reasons, SB Acoustics measured from mass method gives me 0.06, which is extremely low. I don't know why. But we can say that Status inductance-wise is similar to SB17, and the DP has like, what, 3 times higher inductance, similar to the Fatal Pro. So Status has much lower inductance. And the mid-range is very similar. We have FS of the Status 165, very similar to factory specs. The DP is a lower 100 Hz FS, 106. Now QTS is high for both, status and the DP was 0.8, so it's extremely high QTS. It's ideal for in-dash locations. If you're gonna put these drivers in pods, it's not gonna be ideal for them. You're gonna have a very peaky response. Peerless has a lower, however, suited for IB as well. And this is the boss, the shitty one that I have, is 1.3 Q, so it's even a higher Q. For these, let's have a look at BL as well. So motor force. The boss, the shitty one, very small BL, 2.2, similar to the DP. So it's a ferrite magnet, it's not neodymium. The status has a neodymium magnet, and it's like 50, 30% higher. It has 4.1, 3.9, so much higher motor force compared to the DP. DP is smaller. And it's in a comparison with the Peerless. The Peerless has a massive motor, massive magnet on the back. And you can see here that it's a big BL number. LE, again, inductance. So for mid-ranges, they have much higher and much lower inductance compared to the mid-bass because it has a smaller coil. The Peerless 0.16, so measured is a bit higher. However, state is 0.03. It's extremely low inductance. DP slightly higher, 0.06, twice as high compared to the status. So status again with low inductance, ideally in theory lower distortion. Another thing is the SPL calculated 1 watt 1 meter. These are calculated like theoretically, they're not measured. As you can see, they're quite lowish. When I was testing the Peerless driver against the Fatal Pro 4FE and the Satori that has much higher sensitivity, these were the lowest sensitivity drivers that I had, and I said that they measure like maybe 2-3 dB less, and it's very similar with the status and the DP. All of these drivers have theoretically similar sensitivity, so I would assume they will won't give me as much output as I would like, just because, like status for example, is because of the cone. So the cone area in specs is 38 square centimeters. However, if you remove the central pole, which is the face plug that doesn't really count as a cone, it has the lowest uh, cone area from all these drivers. And very similarly with the status mid bass. Again, this one SD is 104 only, much lower even than the SB17. And SB17, we know that it has a massive bezel and little cone. And compare this to the Fatal Pro. Fatal Pro, 150 compared to 100. So that's 50% less cone area the status has compared to the Fatal Pro. And again, the sensitivity kind of corresponds to that. We have status at 86 and we have Fatal Pro at 91. So that's 5 dB, 4 or 5 dB in theory less sensitive. So again, these status drivers, they're not going to be playing extremely loud. And another thing that I did, I have this sheet that I made. And yes, it's a long sheet. It has like close to 300 entries, and all of them were entered manually. And what I did, I have subwoofers mainly, and I have some components as well. So I have here 6.5, 7-inch, and 6-inch drivers, and most of them are like hybrid audio, JL audio, micro precision, Alpine, focal, Hertz, and that kind of stuff. And we just this is very good just for comparison, like in general how the drivers vary. So if you look by the FS, smallest to largest, the lowest FS drivers that I have in this list is like SB Acoustics, obviously 3040. Then Micro Precision has a very low FS. These are my measured SB. And then we go higher where all the other ones. So see like 65, 75, these are the highest FS drivers. So status, they're one of the highest FS drivers from this list. Now let's have a look at moving mass, smallest to largest. So the smallest moving mass, we have hybrid audio drivers, micro precision, only 9 grams. And we know that like micro precision has a very light cone, very light drivers, GLC3, hybrid audio, blah, 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 that kind of stuff. And here we have Fatal Pro has low mass as well compared, and SB Acoustics. And if we go down the list, the Alpine, as I mentioned, has the higher moving mass, very similarly to JLC7s, which is the high end. So again, high moving mass not necessarily mean that the driver is bad, because look, C7s, they're the highest tier of JL. C5s as well, 15 grams. Focal, I think these are flax, 15 grams. So it doesn't mean that's a bad driver, it just has a lot of moving mass. And if we have a look at the BL number as well, and we can see, and this is my theory again, that high moving mass drivers have a lot of motor force. And we can see like the DP, Alpine DP, has one of the highest BL numbers from this list. DP and status as well, here somewhere. Yeah, so that's BL. Now, inductance, I don't have a lot of inductance values because very few manufacturers actually publish this. However, I have a few, and we can see that, again, SB Acoustics, the smallest inductance. Micro Precision has very small inductance. Hertz Milli Pro, Milli Legend, and Status has low. DP is higher, together with a Fatal Pro. I cannot comment about any of these because it's just, they're not there. And very quickly, let's change this to the mid-ranges. So let's untick. If anybody interested to explore this file, I would be happily to supply it for you. Just email me and I'm going to send it to you. So these 3.5 inches inductance, let's have a look. Status, the lowest inductance from all, together Hertz Millilegends, ScanSpeak 10M. What else we have? Yeah, for these we don't have anything, but yeah, status, lowest inductance. Let's have a look at resonant frequency. So these are 4, 3.5, and 3-inch drivers. Micro precision, no surprise, lowest resonant frequency. Peerless, the 4-inch home audio drivers. Status have the highest. It's not a big list of these drivers that I have because I wasn't bothering entering them. But yeah, Focal has a higher. So again, similar to C7s. Status mids, very similar to C7s. And you can see the other parameters similar as well. Yeah, and yeah, I think that's it. So this video was for you to find out how to measure the TS parameters of the drivers, what to look for when you're looking at an impedance graph, and a slight comparison between all of these drivers that I have measured and all of these drivers that I have in here. Again, if you're interested in this file, I have 261 drivers. Most of them are subwoofers. It's very fun to compare. Just sort by something and compare the drivers. Very, very fun. Yeah, so again, thank you very much for watching, guys, and I will see you in the next one.